Hello everyone and welcome to part 7, I believe, of an Astronomer react to the flat Earth alternative to gravity, which is Incoherent Electrostatic Acceleration. We are at part 2, a bit over the halfway point there, and maybe with a bit of luck, I have been making the episodes more close to 20 minutes than to 15 minutes, because I feel like when it's 15 minutes I need to hurry with everything, and I don't like that. Now, yeah, let's continue. I intend to finish today, if that is possible.
Last, we will drop it from an airplane. Not that I have tested it, but I
Okay.
doubt the couch would be much use as a furniture piece after the bowling ball came to rest, wherever that may
Very
be.
true. Also, like, when he talks about dropping stuff, right? I would love to see his calculations about how fast it will be at the when it has reached terminal velocity, and I would love to also see his calculations for how much energy it has, kinetic energy. Love to see those, but I am venturing out and guessing that he doesn't have any for those.
Probably a few floors below the couch, I would bet.
I believe bowling balls break somewhat easily, but that's not the, of course not the topic of debate here.
Now someone might claim a helium balloon does not succumb to these accelerations. But if you remember in the first video, this acceleration is very weak, and potential differences of other phenomena such as temperature.
I mean, you have said that it is very weak, which makes me think. For example, if I were to rub my comb, right, with which I comb my hair, if I were to comb my hair a couple of times and I'm not grounded and the charges can't escape and I let go of my comb, will it just start floating, or will it crash down to the earth with a lot more force than it would have with gravity? Or, and hear me out, does it fall like all the other times? just wondering. Just wondering. Because if it's electrostatic, right? If I charge something sufficiently with sufficient charge, which can be done with non-ridiculous methods, you can use a Van de Graaff generator, for example. Electroboom has built one. If you could charge things to what I think would be way more than the charge necessary to lift it up into the sky. Why aren't we doing that? Because it doesn't work, because the reason for the downward vector isn't incoherent electrostatic acceleration.
Gas pressure, and buoyancy are much stronger. If one places a helium balloon in a vacuum chamber where it is more dense than the surrounding area, it most certainly shows it is affected by the downward bias.
How is it affected if, well, it's in a vacuum? Because in your model, isn't there, or maybe, I guess the particles in your model are not all too much relevant. Okay, no, that's fine. Of course, we here in non-flat Earth land know that happens because of gravity.
Outside the chamber, the balloon will rise, but not at an accelerated rate.
Well, technically, it would. The thing there is that the force that's pushing it up, the buoyancy force of the helium balloon, is not very big, and the balloon has a rather big surface area, so or like wind resistive area, so it quickly reaches its terminal velocity, but it does accelerate for a bit.
The same with air bubbles underwater released by a diver. They do not accelerate up, but are
Well, they have to be accelerated at some point, or else they wouldn't move, would they?
displaced by the water, which is more dense and therefore the matter in the area most affected by the downward bias. It doesn't keep accelerating up because the water around it only needs to travel the distance of the bubble before the potential is equalized again.
I would also be curious to see his calculations for the electrostatic charge of the water and how that is moving. Would love to see that, because water, depending on how much ions it has in it, but salt water in general is somewhat conductive. So I would imagine the charges to move around somewhat freely in salt water. So why would there be some more charges at some place? That wouldn't make sense. In salt water, the charges would equalize quickly.
The process is then again repeated with the water just above the bubble until it reaches the surface and there is no more water to displace it. Last off, I have heard some state the ideal gas laws disprove electrostatic acceleration on gases, and I must admit it makes me...
Well, there certainly are no the ideal gas law. That, mind you, is a simplification, but it works fine enough for most purposes. The ideal gas law does not take into account any kind of electromagnetic effects at all. That is because they are only relevant in highly ionized. They are only relevant in ionized gases, right? Not in the daily air that we interact with, so to speak.
chuckle a bit. Here's a high school teacher explaining why they have to do this and that it is a make-believe place.
Oh god. Yes, flat earthers once again attacking one of the very core concepts of physics that they do not understand for even a second. I cannot wait to do so. Mind you, he is quoting from what I assume is a video from a high school teacher, so it's not necessarily misrepresenting, it's more going to be of a high misunderstanding.
There are an uncountable number of molecules inside this balloon.
Yes.
It's my breath. But whatever the gases are inside of here, guys, this is absolutely chaotic. It
Yes.
defies study.
Well, defies study. That's not an expression I would have chosen. I would say that in order to make predictions for that, you would need to know the position and the velocity of each and every particle in the system, which in your average molar numbers that you have in anything that we find as relevant, like in a balloon, this is absolutely impossible.
Because it's so complicated. You get the idea? So guys...
Well, I mean, it's not complicated, it's rather easy. It's just a lot. Like a whole bunch of easy makes extremely difficult.
The question is, how do we fix this? And the answer is, we go to the land of make-believe.
That's among the poorest wording I've ever heard in use with a science teacher. We don't go to the land of make-believe, we go to the land of modeling and some simplifications that are necessary. And we also go to the land of experimentation, because turns out the ideal gas law was long thought to be the real gas law, not just for ideal gases. There are some assumptions made in an ideal gas, for example, that the distance a particle can travel is very big compared to the diameter of your average gas particle, which is true in atmospheric conditions. That's just one of the many. Also, that another assumption that has to be made for the ideal gas law to work is that the collisions are elastic, so that the momentum is conserved, but the energy is also conserved. For example, that's not make-believe. Those are two very reasonable assumptions that hold true on large scales and on the scales that we interact with so accurately that for the most part, unless you study a subject like thermodynamics or in some contexts aerosol physics, you will not need another one even if you're a physicist.
And guys, this is not stupid and this is not dumbed down. This is smart science. If you've got a system that's so complicated that you can't study it, what do? You simplify the system.
Yes, that I agree with. You have to simplify the system. This is how statistical mechanics came about, that Ludwig Boltzmann came up with.
And guys, that's what ideal gases are. Ideal gases are simplified gases that make our lives easier. Now guys, be clear.
Absolutely.
Do ideal gases really exist? No, but
very close to ideal gases. Of course they don't exist, but it's so close that the deviation from ideal gases in most day-to-day applications is so little that it might as well be an ideal gas.
We treat them as if they exist. And what allows this to be the case? Don't write this down.
I hope this may have cleared up any misconceptions.
I will have to go through. I have opened the tabs in advance, actually. because for a change I just looked at the video for 2 minutes to see what we are talking about today. So I'll explain the gas laws to you in this part.
You may have had on the matter, or at least
It has cleared up no questions whatsoever. It has been more with more things, with no equations. You have not presented any numbers. The mechanism is flawed from the very beginning. How would it work in areas that are very shielded from electrostatic fields? And they don't even have to be fully shielded. They just have to be shielded significantly, like 80% is completely enough that you should notice a significant difference. What about thunderstorms? How could materials that don't react to electrostatic or electromagnetic fields, for that matter, fall just like all the other ones? No answers to all of these questions whatsoever. It's a very unthought out idea, but I believe that we all know that.
help further your comprehension of this phenomena. If you have made it this far and still haven't seen the first video, please click the link below and watch part 1 before asking any questions in the comments below. This is Good Times for All here, signing out. As always, thanks for watching.
Well, you're most welcome. And again, in case ever flat earthers will see this, and I'm not just doing these videos for my self-pleasure. That sounded wrong. Maybe let's not word it like that. If any flat earthers ever see this, it's not like I'm attacking Good Times for All, right? It's nice that they do videos like that. And if I say it's very much not thought out, that's of course not a personal attack. How would it also be? I'm attacking an idea, always. Now, with that said, let's explain gases, shall we? You have the ideal gas law. That's probably a version of the thing that you've learned in school. Some learn it like that. That's more the one that's used in chemistry and aerosol physics. I learned it at university with PV, where P is the pressure and V is the volume, is equal to N, the total number of atoms, where you literally count the atoms. So the small n is the number of moles, so that's more the chemical side of things, times the Boltzmann constant times the temperature. Boltzmann constant times the temperature is you can think of as an energy, right? Because the Boltzmann constant has Kelvin per joule, so there are also other possibilities like that, where you have the Boltzmann constant and the Avogadro constant, which actually is how Boltzmann wrote it the first time. Not important, right? That's the ideal gas law. When you have a PV diagram, so pressure there, volume there diagram, those for the ideal gas, they look like that, right? And that's fine. And essentially what an ideal gas is you have, maybe there's a picture here somewhere. No, there's not. Is the one for the Maxwell-Boltzmann distribution? Yes, that's an ideal gas right here in the top window, where you have a whole bunch of particles that are moving around somewhat not somewhat freely, until they bump into something, and that's how the system is. It is rather chaotic, and after a given time, which can be seen down here, the velocities of the particles, or the speeds rather of the particles, conform to the Maxwell-Boltzmann equation, right? Which can be seen here in this yellowish orange, and you can see that the measured one, I mean, this is of course a simulation, but that this over time conforms more and more to this theoretical prediction that is the Maxwell-Boltzmann equation. The Maxwell-Boltzmann equation gives you the speed distribution for different particles at different temperatures, right? So the masses of the particles play a role, and the temperatures at which they are moving at play a role. And something that I probably should note is that it's asymmetrical. So even though that here is the center, it's not symmetrical. You always have a small, in physics I call it lag. We have a small lag kind of in the higher area. So regardless of what temperature your particles are at, when we're talking about classical physics, I will ignore the extremely low Kelvin area for now, because it's not important to this discussion. You have a few particles that are high energy, or like high speed, if you will. And now, the guy in the video has said that a real gas kind of bears description, which is true in a high school setting, certainly, but not at the university setting, because you have real gases. We know how to describe real gases. You remember the PV curve I showed you for the ideal gas? Those are so-called isotherms. These isotherms are for a real gas. They look the same for high kind of volume, high pressure areas, but the smaller you lower the pressure, you see something's happening. It gets a bit bumpy. And that's due to the van der Waals force, which I will not explain. It's essentially a very weak force between particles due to their, I believe it's charge polarity or something. Yeah, so that's the real formula there. There's a whole Wikipedia article. I'm not going to explain all of it because that would rob us of some valuable time. And you have things like that, for example, where your ideal gas comes down here. This is the van der Waals, what the van der Waals force would predict, and this is the Redlich-Kwong model, which is more accurate even than the van der Waals force, but you can see that the van der Waals prediction is extremely accurate already. So we know how to describe real gases, and that even though there are different models, because it's extremely complicated process with a lot of variables involved, right? Notice though that if I look for charge, oh boy, you cannot find everything. That's because charges only play a role in plasma or in ionized gases, not in your regular gases. How well would you look at that? Also, because he said that he must chuckle because it's not in ideal gas, because apparently the ideal gas is just make-believe. If it was so important, your silly charge idea, if it was that important, then why not include it in the ideal gas law somewhere? Can you do that, maybe? It would be nice, but I'm venturing out and guessing that flat earthers cannot very much, because how would they? They don't really know anything about electrostatics, I believe. With that said, I believe we are done with this video. I will do another video on this where I will calculate for myself. I plan to do a video. If it's too short or if it's not significant to make a video about, I probably won't. But if I feel like it, I will make a video where I show how much charge everyday objects would have to have in order to exhibit the behavior that they have due to gravity. And then we can all laugh at the predictions, because from a very rough calculations, the charges would be very high necessarily in order to exhibit the effects that we see, so everything would be supercharged all the time. Yeah, anyway, enough about that. If you have any ideas what I should talk about next, feel free to let me know. And other than that, thank you very much for watching. This actually fits very well. Thanks for watching. And consider maybe possibly leaving a like, or dare I even suggest subscribing. Until that, we'll see you in the next video, so have a nice time, and I'll see you in the next one. Bye!